So yesterday I have explained how the linear regression algorithm is finding out the coefficients, right? So it's a linear algebraic approach. Right? Linear algebraic, that there is a formula x transpose x whole inverse x transpose y. But the problem with that formula is it cannot work with a huge volume of data, and it has got a dummy variable trap also. Why are we worried about dummy variable trap? There may be two cases where we may get into dummy variable trap. One, we may be creating dummy variables for maybe 3-4 categorical columns. Right? I'm saying x1, x5, x6, and xk. Right? Maybe xk plus 3. Some 5 columns we are doing dummy variable creation. By mistake, one or the other column may get into a correlation. The chance is there, right? By chance, it may become correlated, right? The chance is there. Do you agree?
Yes.
Do you agree with my statement? Right? You can see my screen, right?
Yes, sir.
Okay. So there is that chance. That is one problem. The second problem is when you are handling maybe 200, 300 columns, you cannot actually check correlation of all the columns between input variables and all that. Even though you do heat map, it will be a bit confusing, right? So you may miss sometimes. So these two are, the model may get into dummy variable trap, and the ultimate coefficients may not be found properly. That is one problem. The second problem is it cannot handle huge volume of data. The advantage is that in a single shot you will get all thetas. Okay. To avoid this problem, by now I see that not able to handle huge volume of data is a big problem. Do you agree? Not able to handle huge volumes of data is a big problem.
Yes, sir.
Yes.
Right? Why? Because in industry, it is all huge volume of data only. Right? Not, you will not find small data sets. Especially we see that in image processing and text processing. Even though the data set is small, when you try to convert it to numbers, it will become a huge data set. Okay? So the algorithm should have capability to handle huge volume of data. Every algorithm will every algorithm have this capability? No. Linear regression, logistic regression has got the capability because it is using stochastic gradient descent algorithm. We are going to learn that. The advantage of using stochastic gradient descent is that it can handle huge volume of data. This is the basis for deep learning also. Actually, deep learning is starting here. This is the basis. If you understand this, deep learning will be very clear. Okay. So focus well. Any questions you ask, I'll answer. Okay. The way stochastic gradient descent works is, let me try to take a whiteboard and explain. So so yesterday when we saw what happened, they actually took that whole data and then formed the equations like this. Or as a layman I am talking equations, but in reality what is happening? This is what is happening. X transpose x whole inverse x transpose y is what is happening. It is substituting all the x's, all the y's, and finding thetas. Okay, that is how it is happening in normal equation based approach. In gradient descent approach, right, how gradient descent works? Suppose that your data is like this. Your data is like this. Suppose that there is only one x and one y. Okay. We always take one x and one y to explain concepts, and we need to visualize the bigger problems. Okay. So x here, y here. Suppose that your data is like this. In normal equation based approach, right? Let me take this color for normal equation. Normal equation approach, we substituted all x's and all y's into x transpose x whole inverse x transpose y. We got a straight line. We got the coefficients. What is coefficients? A straight line, right? What is coefficients? A straight line, like that. I got it in a single shot. Okay. But in gradient descent, how it works is, now we are trying to understand gradient descent. Let me take another color. Why we call it as gradient and gradient descent, I'll explain. And in gradient descent, how it happens is, it randomly draws a line in the space like that. Some line. Okay. When I say some line randomly drawing, in mathematical equation, what is it doing? Suppose when here, right? We found, when you substitute x and y here, we got an equation like y cap is equal to 10x plus 5, maybe. Some equation we got. Okay. But in random, in gradient descent, I said that the algorithm, the solver, we call these as solvers. Normal equation and gradient descent, we call them as solvers. So gradient descent and normal equation are solvers. This solver is drawing a line randomly in the space. When I say randomly in the space, what is it doing? Can somebody tell me? In terms of the equation. In terms of the equation. In terms of thetas.
Maybe it forms a reference equation to start with.
Reference equation to start with means maybe y cap is equal to 5x plus 5. Some, some theta it chose, some theta 0, some theta 1 it chose, and did an equation, right? Randomly drawing an equation or randomly choosing theta is same. Do you agree? Randomly choosing an equation. Do you agree? Agree, right? Right. So now what it does is, it tries to move this line, right? It randomly drew this line, the gradient descent algorithm randomly drew this line, and it starts moving the line like that. Ultimately it reaches here and it stops here. When it reaches here, right, to the global minimal error place or the best fit line it reaches, it will actually draw there only, on that line itself only. That is how the gradient descent algorithm works. How is it working? What are the equations? I will show you in a moment. But the essence, how gradient descent is finding the best fit line. What is our goal? We need to find best thetas, either using normal equation or gradient descent. But normal equation using single shot approach, linear algebraic approach, which needs huge volume of data. Gradient descent is not using the single shot approach, but it actually can not gradient descent, but stochastic gradient descent. We derive another approach called a stochastic gradient descent from gradient descent, which will not use huge volume of data and will be able to find out the best fit line. But the way it works is, it draws a random line in the space and it moves the line in such a way that it actually reaches the global minima at one point in time. Okay. By gradient descent algorithm. Suppose that you don't have the algorithm and you wanted to draw lines like this, random lines like this. Do we know whether when we will be reaching the global minimal or best fit line? Suppose that an algorithm is not there. What I am saying is, this is a solver or an algorithm which actually draws a random line like this and moves the line in a systematic way, in such a way that it actually reaches the best fit line, right? Systematically it is moving, mathematically it is calculating, and it is knowing that the slope here, the error here is high, the error here is little low, the error here is even lower, even lower, and it is the minimal error. Okay, got it? The algorithm is moving like that. If you don't have a systematic approach, you may be drawing a line here, line here, line here, line here, line here. You don't know whether you reach global minima or not. You may do 1 million lines. Out of all those lines, whichever is giving minimal error, you may choose it. But still you don't know whether that is the best fit or not. So the gradient descent algorithm is giving you a systematic way to verify whether we are moving in a right direction, and whether we reach the global minimal error place or the best fit line place. Okay, how gradient descent is working, you understood, right?
Sir, it's better to, you are actually showing a line as an example for modeling. Maybe it may be better to even to consider some curve kind of thing, and maybe if we can explain from that point of view, that may be better, because in reality it may not be straight line, trend may not be straight line, it may be some curvy.
We will come to curves, sir. First we need to understand straight line.
Okay.
The other thing is, right, you should not be, you should not be worried about the curves. We can actually make them work. Whether it is a curve or a straight line, we always look at the error. So first try to understand this. Okay, first try to understand this. We'll go there. We will be solving curves only. We will be solving very complex curves. Don't be worried about curves. Just understand this. You understood this, right? This part, right? This part is clear. Anybody has got any questions? So now, right, now what is happening here is the gradient descent algorithm is actually looking at the error, right? What is error? You took this line and then you predicted on the line, right? And then calculated error, and again you adjusted these weights, right? The second equation is going to be y cap is equal to slope is high, right? 6x plus 5 and r 6x plus 3, right? Again it's going to calculate, y caps and calculate errors, right? And see the error, it is low. Again y cap, right? 7x plus 4, and again it is going to calculate like that. With each equation it is calculating error and checking whether we are moving in a right direction or not. The basis for gradient descent algorithm to move towards global minima is the error. Okay. Whether it is curve or a straight line, the basis for the algorithm is going to be the error to move towards the global. So while understanding, right, we will understand with simple equations, and then we need to visualize. If we take the curve and then try to explain, right, I will not be able to explain. First thing. Second thing, you may get confused. Right? Maybe you can grasp it, but some people may get confused. Okay.
Okay.
So I am taking simple approach. I think by end of the gradient descent algorithm, and maybe further, right? Maybe in a two weeks time frame, right? You'll get very clear picture. Okay. So that's how it works. Okay. So let us try to jump in and look at the slides. I actually took a data set, a simple data set, and try to visually show you how it is working actually. Okay. I already opened it. So there is a representational thing we need to understand a little bit. Now we'll come to representations later. But let us try to see how it's working. See this? I have taken some data set. This is real, real data set in the sense, generated data set. Okay. The red dots are the data. And when I initiated, right, when I initiated the gradient descent algorithm, it actually took the theta as 100. I said it is going to choose theta randomly, right? It took theta as 100. when it took theta as 100, and the equation is also the equation I chose is y is equal to theta x only. There is no theta 0. Why? Because if I take theta 0 also, it is going to become a three-dimensional picture. This is going to become a three-dimensional picture. Okay, so we need to have not this one, right? The error graph is going to become three-dimensional. I'll talk about that later. Okay, to simplify the things, I have taken the equation as y is equal to theta x, no intercept. See this is going through origin, almost like origin. Right? So I took the data, and algorithm chose 100 as the theta and drew a line. Now it actually calculated error. If you look at the second graph, right, I have taken theta on x-axis and error on y-axis. J of theta is nothing but the cost function. Let me show you that notation. See this here. Original equation is like this: theta 0 plus theta 1 x. Okay, there are two parameters, and the cost function is, what is cost function? Error, right? What is error? Predicted value minus actual value whole square, sigma I is equal to 1 to m. Do you remember this? What is this? Do you remember this formula?
RSS.
RSS, this is right. Residual sum of squares. Residual sum of squares is the formula, right?
Yes.
This is the error. Okay, this is the error formula, and I am doing 1 by m, right? 1 by m is the average, right? Mean squared error. Now I took 2 because of some reason. I'll show you why 2, right? Why 2m. Okay, so that is the actual equation. So our goal, what is the algorithm's goal? It started somewhere here. Give me 1 second. So no, it started somewhere here, and we the algorithm got to know, the solver got to know that the error is high, and it did some experimentation. It actually tried to find the next theta. How it is finding, we'll see in a moment. And it found that the error reduced. The goal of the solver is to reduce error. While reducing error, it is finding the best fit line. Okay. The consequence of finding, reducing error is the best fit line. Did you understand the statement? The consequence of reducing error is the best fit line. Did you understand? No, do you understand the statement there? The consequence of reducing error is the best fit line.
Yes, sir.
Right? The algorithm is trying to reduce the error. That's it. It is not trying to find the best fit line. It is trying to reduce the error, ultimately it found the best fit line. Okay. So it is like this. You need to achieve, or deliver a project. Right? What you will do, you will not sit and try to see deliver. You will actually work on the project. You work and try to reduce the, test errors on the in testing. Ultimately, the project actually becomes best, and you deliver it like that. The algorithm is trying to reduce the error. The consequence of reducing error is the best fit line. Okay, that's the statement you need to remember. So here, the equation is this one, which we need to find. To find that one, we took some random thetas, and then we calculated error, and the algorithm is trying to, reduce the error. Goal of the algorithm is to reduce the cost function. Cost function is a very important concept. It will be there with you throughout your life. Okay. So deep learning, we always talk about cost function. So I simplified this equation for a reason. I'll show you why. I'll explain you why I simplified it. Instead of taking theta 0, I took only theta 1 x, only one theta, one coefficient. Only one variable is there. Now you see the cast function became a little simpler. Theta 1 x minus y. I kept superscript I here, right? Not subscript. Superscript I actually denotes the row. Okay, first row y, second row x, second row y, third row x, third row y, right? So when you do theta and x, that is the prediction, y cap, right? This is the y cap. H of x is y cap. So we are calculating error, and then the algorithm is trying to minimize. So the original equation is this one, when you have 1x, but I reduced it, I simplified it for understanding purposes. Okay, so y is equal to x square. Is that a convex function? Do you know what is convex function? Y is equal to x square. See this? Can you see my screen?
Yes.
Yes, sir.
Right? Y is equal to x square is a convex function. Convex means, convex, concave, you remember, right? Like a bowl. Why bowl? Suppose that when you started with your random theta, random coefficient, error may be somewhere there. Dot, where is the dot, right? The dot is here, right? So error may be somewhere there. And the algorithm will actually try to reduce it in such a way that it reaches here. And how will it know it reached here? If you take some slope here, right? Let me try to take a screenshot. If you look at a slope here, if you try to draw a line like that, right? There will be slope. Here also there will be slope. Here also there will be slope. But here the slope is 0. Do you agree? Do you agree? The slope is 0 here, right? Right? Do you agree?
Yes, sir.
So suppose that on x-axis you have theta and y-axis cost function. For first theta, right? First theta is 100. You got some slope for the cost function. For second theta, you got some slope. Third theta, you got some slope. Slope is reducing. Error is reducing. Slope is reducing. At one point in time, it became 0. Slope became 0. So the algorithm looks at the cost function's slope at given theta. It chooses random theta, looks at the cost function slope, and tries to reduce the slope in such a way that it reaches 0. The slope reaches 0. Okay, that's the next point. First point is it randomly chose theta, drew line, and then found out the cost. And second point is it is trying to reduce cost in such a way, reduce error in such a way that the slope of the error becomes 0. Okay, so I'll explain more about this in a moment. Don't be worried about it. So let me go back to that time, whatever this. So if you come here at 100, we had, at 100, right? 100 point, I did not do it. We had some slope. Okay, we used that slope at 100. The slope of the tangent is, I did some derivatives and all that here. Don't be worried about those derivatives, right? At 100, the slope of the tangent was 58,000, no, 5,87,773. Okay, I took that slope and reduced it from 100, right? What I need to do? I am somewhere here. 100 is somewhere here. I need to move to this place. Right? I am trying to find theta. I am trying to find best theta. The random theta chosen was 100. I need to move slowly to this place. Okay. To move the algorithm to this place, what I am doing? I am reducing that slope from 100 by multiplying with some number. Don't be worried about this number also. I'll explain. Okay. By end of this class, right, you will get more clarity. Even if you have, more confusions, right, I'll take one more class. Don't be worried. So I am taking the slope and multiplying with this number and reduced it. See that? 100 reduced to 70. Now in the next iteration, At 70, I calculated slope of the tangent, we call it as. Okay. Slope of the tangent, we calculate. When I say tangent, right, it is just touching the curve. The line is just touching the curve. Okay. I calculated slope. Again, from 70, I subtracted the slope by multiplying with some coefficient. I'll talk about this coefficient in a moment. Don't be worried. Again, it became 50. At 50, right, what became 50? Can somebody tell me what became 50?
Theta.
Yeah, theta became 50. Okay. Theta is the one which is reducing, right? At every theta, we are calculating slope and trying to reduce the slope here, right? Reduce the slope here. So reduce the theta in such a way in the direction of slope. Sorry, the statement was wrong. In the direction of slope, we are trying to reduce the theta. So I reduced theta, it became 50, right? Again, it became 36, 27, right? 20, right? Like that. See that it is actually no. It started somewhere here. The error was there when it was 70. Error was there when it was 50. Error was there when 36, 27, 20, right? 16. The error, is actually reducing. What is on y-axis? Error. We need to remember that. So if you look at the diagrams from beginning, the line was somewhere like that when it was 100. 70, it reduced. 70, 50, right? We are not looking at the line. We are looking at the error only. The consequence of reducing error is the best fit line. You look at this only. Okay. Automatically this line will actually come to the best fit place. The screen is changing rapidly, right? Is the screen changing rapidly?
Yes, sir. It's good.
Yeah.
As I
It's
move, you can
changing.
see, right? Huh?
Yeah.
Okay,
Yes.
good. Okay. So when we are the algorithm is focused on this part, automatically this is getting fixed. Okay. Move like that, like that, like that, like that. See that? By the time it reaches somewhere here, it actually is almost close. This is on a real data set. I executed it. I executed it and took printouts. Right? See that here? So by the time the theta reached here, where the slope of the tangent is 0. Will we, if you look at this graph, right? Are we getting 0 error? Are we getting 0 error?
No, sir.
No, we will not get 0. We will not get 0 error. Yeah, most of the cases we will not get 0. So the algorithm is working like that. The gradient descent algorithm focuses on cost function's slope at given theta. Right? Cost function slope at given theta and reduces your theta in the direction of the slope. So after 70 iterations, it actually reached ground. It reached like this. It started somewhere here, right? Moved, and it moved here. And now here, right? It actually stuck here. It is not actually going beyond that best fit line. How is it working? Because of the formula we are using here. See this? This is the theta. This is the theta. This is your coefficient. I'll talk about this coefficient in a moment. Right? This is your slope of the tangent. Right? The slope of the tangent is almost 0. And you are multiplying that with another number which is almost 0. This number is almost 0. It will not move. Right? This number, right? This minus 0 is going to be this only. So when it reaches the global minima, it will not go anywhere. So that is how the constraint the equation. This is called as gradient descent algorithm. This equation is the gradient descent algorithm, which actually takes the theta minus alpha into slope of the tangent at the given theta. Okay, that is the gradient descent algorithm. Any questions here? I actually showed you by drawing here with my pen. Whatever I drew is true. That's what I am trying to prove. Any questions here? If you're all clear with this, right, I'll move on and try to show more.
It's really interesting, sir.
Yeah, it is really, really interesting and exciting. And if you see stochastic gradient descent, right, it is even exciting. And this is the basis for deep learning.
But
Here we are
one
using
thing, sir, like one thing, sir, this many iterations may degrade the performance, right?
degrade. It may take time,
Hmm.
but you will be able to handle huge volumes of data. That is our goal, right?
Okay. Hmm.
Right. In the industry, you have huge volumes of data which is unstructured and never explored. That you are trying to solve that problem with artificial intelligence.
Okay.
Right? That is our goal. So our purpose is served. That's where we are actually going to use this gradient descent, stochastic gradient descent, basically, not gradient descent, but got it.
Yeah.
So here, the focus is always, the algorithm's focus is on this area, theta and cost function, not on x and y. X and y will get fixed automatically. No, not x and y. The equation will get fixed automatically when you actually move it in right direction and make the reach theta to a place where the slope is zero. Okay. Theory, now we understood as a layman now. Right? Till now, we understood gradient descent as a layman. Now let us try to understand it as a mathematician. This is what the math. Now AI needs mathematics. This is what is mathematics, right? I'll try to explain mathematics now. We need to understand this. We need to remember this, right? So let us try to understand mathematics. So where to start? I'm actually thinking. So I actually showed you that, look at this part only, simplified part. H of x is equal to theta 1 x1, theta 1 x, and only one parameter we need to find. And the algorithm is looking into this cost function, right? 1 by m, sigma I is equal to 1 to m, y cap minus y whole square, Okay. We took this cost function because we wanted a convex function as the cost function, because at the bottom of the convex function, the slope is zero. We intentionally took this cost. Why not absolute error? Why not something error, some other cost function? Only the squared cost function we have taken because we want the cost function should be a convex function where the slope of the tangent becomes zero. When slope of the tangent becomes zero, we know that we reach the global minimal error place, and from that place we should not be moving the line. To accommodate that, right, the researchers or whoever found the gradient descent algorithm took the convex function as the cost function. Okay, understood? Why convex function a cost function? Okay, so goal of the algorithm is to minimize the error. Okay, so that is one point I wanted to reiterate. And the formula to calculate, or the gradient descent algorithm's formula is next theta is equal to current theta minus alpha into cost function. I'll talk about alpha at the end of the class. Okay, cost function's slope at theta. That's what we have seen so far. Right? Current theta minus alpha into cost function slope at theta. Okay, so or current theta minus a derivative, partial derivative. This is okay. Dou j theta by dou theta. Do you remember derivatives? I'll anyway reiterate the derivatives and calculus a little bit, but you remember, right? So current theta minus alpha into dou j theta by dou theta. The cost function's slope at theta can be calculated using derivative of the cost function with respect to theta. See this? Cost function's slope can be calculated by calculating derivative of the cost function. Remember that, okay? Derivative of the cost function gives you cost function slope of the tangent. Right? I said that there is a tangent here. I need to find out the slope. How can I find out? You have a cost functions equation. You calculate derivative of the cost function and substitute this particular theta into that derivative. Whatever number you get is the theta, is the slope of the tangent at the theta. See this? Dou j by dou j of theta by dou theta is equal to this one. How do you calculate? I'll actually show you. The equations also I'll show in a moment. Okay. And here also, see that? See that? This is called as gradient. The slope is called as gradient, and we are descending our theta using gradient. That's where we call it as gradient descent algorithm. Got it? Slope, another name for slope is gradient. Okay? Using gradient, we are actually descending. What is descending? Error descending. Okay? Line moving to best fit. Error descending, line moving to best fit. Okay? So that is how it is working. And y derivative, I'll explain in a moment. Okay, must do simultaneous update. If you have multiple thetas, right, you should not be you should not be doing theta 0 is equal to current theta 0. Let me try to draw this and explain. If you have multiple thetas in real time, you will have multiple thetas. In real time, right, you will not have one theta, and doing this kind of a simple thing is not the not the real time thing, right? You will have multiple thetas. If the implementation is already there, no need to implement, but we need to understand the concept. Okay, so in real time, right, you will have multiple thetas. If you have multiple thetas, you should not be doing theta 0 is equal to theta 1 is equal to. Suppose that you should not be doing like this. This is a wrong approach, because what happens is, in your equation, right, what is your hypothesis function or the cost function? In your equation, you have theta 0 plus theta 1 x1, right? So when you update this theta 0 and substitute into this, and after that you update this, what happens in theta 1? In theta 1's cost function calculation, you will have theta 0 also. You will be using that, right? While calculating gradients at theta 0, theta 1, you will be substituting updated values. When you do that, right, what happens is, in the this is cost function, this is like this is the gradient descent algorithm, and what happens is the line will move a little down, again a little up, little down, little up, little down. Sometimes it may happen down and up may stay here. So to avoid that problem, you need to update both simultaneously. Simultaneously means, let me take simultaneously means right, like that. You need to take the values into temp variables, these updated values, updated theta values into temp variables, and update them at one shot. If you do this, right, what happens? In this equation, old theta 1 is used. In this equation, old theta 0 is used. Right? Got it? That way it will actually move to the global minimum only. Okay, don't be worried about that. Simultaneous update. We'll talk about that later also. Any questions there? You can ask if you have. Okay, don't be worried about it. If we go into that, right, we may get confused. Don't go into that. Let me go forward and try to explain. So I said that the slope of the tangent is the derivative of the cost function. How? We need to understand, right? I said that slope of the I said that this is the slope of the tangent at the given theta, right? Slope of the tangent at given theta. I said that is nothing but the cost, the cost function derivative at a given theta, right? How? So suppose that, right, this is your cost functions curve, and for different thetas, this is the curve, right? Suppose that I have taken one theta, one random theta, 100, okay, or maybe 70, and that dot is here, right? Why that dot came here? Cost is on y-axis, right? So I suppose that I drew a tangent here. I drew a tangent here. And imagine that on that dot we have two dots, right? Dot itself is very small, right? Dot itself, the area of dot is 0, right? In mathematics, area of dot is 0. But suppose that the dot is having some area, right? On that dot you took two dots and drew a line. When you have to draw a straight line, you need to have two dots, right? Do you agree? When you have to draw a straight line, do you need to have two dots?
Yes, sir.
When you have to, draw a straight line, do we need to have two dots? Guys?
Yes, sir. We need to have two
Right.
columns.
So I
Yes,
took
sir.
two dots on this dot. Right. Dot itself area is very small. So I magnified it. See this? I wrote it as magnified. When I magnified, right, it looks like this. Okay, two dots on the dot and the straight line drawn there. That is called as tangent. When you say tangent, it is just touching. It is just touching the curve. We are actually trying to calculate slope of the curve. We cannot calculate curve slope. That's where we took a tangent and trying to calculate slope. It is called a secant line also. Secant line also. So to calculate slope, what you need? Height and width, right? Do you agree? To calculate slope, you need height and width, right? I'm calculating height here. How do I calculate height? Theta 1, right? Started somewhere here. Suppose that theta 1 started somewhere there. And I said that I took one more dot, right? That dot is h distant, right? Theta plus h, right? This h is very minute. This h is very minute. I took that number, right? Theta 1 and theta 1 plus h. At theta 1, I calculated cost, right? And theta 1 plus h, I calculated cost. The difference between the costs is the height. Do you agree? This height. Do you agree? Any questions there? Any questions?
No questions.
Yeah. J of theta 1 plus h minus j of theta is the height. What is the width? H. Right? The difference between theta 1 plus theta 1 plus h. What is the slope? This is the slope. Right? J of theta plus h minus j theta divided by h, where h tends to 0. Do you remember this? I think it's been a long time since you studied calculus. But do you remember this? J of theta plus h minus j of theta divided by h, where h tends to 0. Do you remember that? No?
At least I know. We know the slope, how to calculate this slope.
Yeah, we know the slope, but this is slope. You got that point, right? But this is something else also. It's nothing but the derivative of the cost function with respect to theta. Limit h tends to 0, right? I think let me try to do like this. Limit x tends to 0. F of x plus h minus f of x divided by h is nothing but derivative of d f of x by dx. Do you remember this? Df of x by dx, right? Remember, right? No, that's okay. So this is the calculus you need to know for total AI. The calculus you need to know is limit h tends to 0, f of x plus h minus f of x by h is derivative of the cost function. So when I try to calculate slope of the tangent, the formula actually is the derivative of the cost function with respect to theta. That's where I am calculating derivative. That's why to calculate slope I am calculating derivative. Got it? Using that to reduce, I am reducing slope of the tangent from the current theta. Reducing slope, reducing slope, reducing slope. You see this here, reducing slope, reducing slope. To calculate slope, I am using derivative formula. Why derivative formula? Because it is whatever the slope of the tangent is the derivative formula. We got to know that now. Any questions? Understood? Why are we using derivative there in the what to call it as a gradient descent algorithm? Understood? Understood?
Yes, sir.
Right. I explained this thing. Theta is equal to current theta minus alpha into derivative. I said cost function slope at theta, and or I said this one and this one are one and the same. The derivative and the cost function slope at theta are one and the same. Why? This is the proof. Okay, this is the proof. This formula actually is the derivative of the cost function with respect to theta. Okay. So now you understood what is gradient descent algorithm, how it is working, what are the formulas, why those formulas, why the derivatives and all that. Okay. Any questions so far? Okay. So you are good. Now I will go into notations. Okay. Suppose that this is your original data. Okay. Original data means row 1, row 2, row 3 and so on, row m. Right? This notation you need to understand, because in deep learning and other areas and the papers, right, they actually represent like this only. I am taking classes not just to explain something and leave. These are fundamentals which will be useful throughout your life. Okay. So even if it is boring or not understandable, just try to spend some time and try to get it. Somehow you get it. I think from the 1st of December, whatever classes we have taken are all important. They'll be there with you throughout your AI career. Don't ignore anything. From the beginning, it is all important, but it is kind of 99% important. This is 100% important. Okay. So here, row 1, row 2, and so on, row n, and x1 to xn. Um, in some cases, right, we represent row as a vector. When I say vector, right, let me try to draw something and explain. One second. So when I say vector, right, if you know, I think you know vector algebra. There is an x and there is y. Okay, and you have a data point. Right? There is some value, maybe 2, 3. Right, 2, 3. This is a data point, we say, right? When I say vector, right, it will have magnitude and direction. From origin, you try to draw a line and put an arrow like this, then you say it is a vector. The same data point, you say a vector. Vector will be generally represented as 2, 3, like that. Okay. As a column, it will be represented as a vector. A data point is represented like this. When you say it is a vector, it will have magnitude and direction. How do you calculate magnitude? Square root of 2 square plus 3 square is the magnitude. Right? Pythagoras theorem. This is 2, this is 3. This is this right angle triangle. Right? This is going to be square root of 2 square plus 3 square. Right? Got it? So this is called as vector. Okay. So in some cases, right, we represent our data like this. So each row is taken as a vector. Right? This is row is taken as column here, because I am saying it is a vector. First row, second row, third row. There are m number of rows and n number of columns. Got it? I flipped it, transposed the original matrix and trying to show. There is a reason for this. I'll talk about the reason in a moment. Till here we are good, right? Till this point we are good. Are we good?
Yes, sir.
Okay. Then why same? Why 1 to m? Now there is a notation called as theta transpose x. Suppose that you already know thetas. Suppose that you already know the theta values. Okay. And we have got one new row to predict. See this here? x0, x1, x2, x3 and so on, xn. And in the superscript I kept I. That means it is row. Right? First column value in ith row, second column value in ith row, third column value in ith row, fourth column, nth column row in row value in ith row. See this here? 1, 1, 1, 1, 1, 2, 2, 2, 2, 2, m, right? Superscript in brackets is always about row. Subscript is about column. Okay. So ith row came in and you need to predict. When you have to predict, what you need to do in linear regression? You already know thetas. You have got a new row and you need to predict the values. You need to make a prediction for this particular row. What you will do?
We'll place the x.
We substitute the x values in the formula.
Yeah, x and theta values into the linear equation, right? We call that as linear combination. Linear combination of x, we call it as. Okay. So you know thetas, you know x's. You will put it into this formula, right? Theta 0 into x0i, theta 1 into xni, theta 2 into x2i, and so on, theta n into xni. You do this, but this can be done using matrices. If you want to do this, right, you may have to write 2 for loops, or if you don't know matrix manipulation and numpy, you may have to write 2 for loops, or some kind of logic you need to write, not for loops, some kind of logic you need to write to multiply these two values and sum them up. But you can do that in a single shot. Theta transpose x. If you transpose this, what happens? If you transpose, suppose that this is a column matrix, this is a column matrix, and the dimensionality is n plus 1 by 1 and n plus 1 by 1. If you transpose this, what happens?
That will become row matrix.
Yeah, row matrix, right? And the dimensionality becomes 1 by n plus 1. Now you can multiply this matrix with this matrix, right? Because the number of columns in the first matrix are equal to number of rows in the second matrix. When you multiply, what happens? This theta 0 multiplies this x0, this theta 1 multiplies this x1, theta 2 multiplies x2, theta n multiplies xn, and it will actually get summed, right? Matrix multiplication, you know, this row multiplies this column and it sums it and calculates one value. The outcome of the matrix multiplication is what? 1 by n plus 1 multiplied by with n plus 1 by 1 is 1, right? M by n into n by p is equal to m by p matrix. The outcome of dimensionality is going to be m by p, right? So it is 1 by 1 matrix, right? The outcome is 1 by 1 matrix. What is that? The predicted value. Using matrices, you can actually calculate predictions. After finding the thetas and x's, using matrix manipulation, you can actually find out thetas. So when you represent your row as a column, you will get this flexibility of calculating theta transpose x and calculating the predicted value. Now I can say theta transpose x is the predicted value. Can I? Can I?
Yes, sir.
Right? That is one advantage of transposing the x into vector matrix and row vector matrix and then using it. I'll show in a moment, more in a moment, right? Theta transpose x is a matrix way of calculating prediction. Theta transpose x is a matrix way of predicting, making prediction. Okay. Now, right? Suppose you see this, I've got the whole data. Right, I already transposed my x and representing it as x, right? And then theta also I transposed and multiplied these two, right? 1 by n plus 1 and n plus 1 by m. Total data I have taken. Here I have taken only one column, sorry, one row and one theta set multiplied. I know the theta set, same theta set I have taken, and I have the total data. I want to make predictions for total data. If I do theta transpose x, right, I'll get predictions for all m number of records. Do you agree? This row multiplies this column. That's going to be first row prediction. This row multiplies this column. That's going to be second row prediction. Y2 cap. This row multiplies third row. That is third row. This row multiplies mth row. That is mth row's prediction. Y1 cap, Y2 cap, Ym cap. Do you agree? Do you agree?
Yes.
Understood?
Yes, sir.
Right? This is called as vectorized implementation. This is how This is how the algorithms actually do the predictions behind the scenes. Behind the scenes, the algorithms are using theta transpose x or matrix multiplication to make predictions. In deep learning, right, these matrix multiplications are exploded like anything because we are going to use many algorithms. Right here, we are looking at one simple linear regression algorithm. There we will take multiple complex algorithms, linear algorithms, or polynomial algorithms, and then do matrix manipulation. The matrix manipulation is going to explode like anything. What is the advantage of vectorized implementation? It reduces number of iterations, and by that way, right, it improves the performance of the model. Okay. Got it?
Yeah, so far we just started with some theta and then we predicted corresponding y values. That's where so far we reached it.
No. We actually understood how gradient descent algorithm is finding best thetas. Right? We started somewhere here. I will show you one video in a moment. Right? By the time we reached here, we found best thetas. This line, right? It is actually modifying this line and reached here. The best theta. What is the best theta here? Where is the theta? I don't know. Yeah, best theta is around 6.28 is the best theta. 6.28 into x. We found best thetas. Now to make predictions on the whole data, how can we use matrix manipulation? That's what I'm trying to show. Right, on a single row, it is a theta transpose x, xi, right? On a whole data also, theta transpose x. This theta transpose x is the way to calculate predictions of whole data set in a single chart after finding best thetas. Got it?
No, it's at least for me it's not that clear, sir. Now at least in the screen, what you are showing us is we have some theta values to start with, and for all the rows, each of the corresponding rows, we can find the predicted values.
Yeah, that way also you can take. Or you know best thetas, then also you can do that, right?
No. We need to start with some theta. That's what you said. That's how algorithms will do. They'll start with initially some theta.
Yeah.
And we calculate all the predicted values. So then so to pick up the next theta, we need to know the slope. To find the slope, how do we know first of all the slope?
When you know y caps of all, you can calculate error, right? If you look at this formula, this is y cap. You can see the cost function, right? On the screen.
Yeah.
Right. What is this? Theta transpose x. This is.
Okay.
Right. For all the rows, right? From I is equal to 1 to m, all theta transpose x's you have. All y caps y's you have. You subtracted, you summed it up, squared it, summed it up. That is the error, right?
Correct. That is the error for one theta, right?
N thetas also. That's what I showed you. Here, see this? N number of thetas also the same formula.
And how do I get the second, let's say second theta, how do I get it, sir? Can you please?
Yeah, you know the error, right? You know the error, right? Here you know the error, right? So your theta is here, your error is here. You calculate the slope of the tangent by substituting your theta into the cost function's derivative. You have this cost function. Can we calculate derivative of it? Let me try to show that. I think your question is right. Let me try to show that. There will be some confusion. Gradient descent algorithm, there will be some confusion. That's where I take around 2-3 classes for this. Don't be worried. You are doing good. Okay. So your cost function, I am taking for one row, right? Your cost function. Right? How do you find how do you find next theta? That's the question, right? So j of theta is equal to I am taking only for one row, Okay, theta x minus y whole square. Okay, so if I expand this, what is this? Theta square x square plus y square minus 2 theta xy. Okay, now I am saying I need to calculate derivative. Right? Derivative of j of theta by j theta, because I need to substitute that into this formula. We'll talk about alpha later. Okay, I know 100 as my current theta. Okay, what is j of theta? Derivative of j of theta. If you calculate derivative of this, right, 2 theta x square. Do you agree? When you calculate derivative of theta square x square with respect to theta, theta becomes variable, the multiplier becomes constant. That is calculus, whatever. This is constant. Theta square derivative with respect to theta is 2 theta. Okay, and y is a constant. When you calculate derivative of a constant, it becomes 0. Okay, plus 2 theta x, so it becomes 2xy. Derivative of theta with respect to theta is 1. Okay, so 2x y it became.
It's minus 2x. Yes.
Yeah,
Minus
minus. Now I can actually take 2x as common, right? It's going to be theta x minus y. What is this theta x? What is this theta x? Y cap, right? Predicted value, right?
Yeah, yeah.
Right? So this is the derivative formula. Now you know 100. What is 100? X. You substitute x here. 2 into 100. Y cap already you know because you calculated the theta transpose x. You substitute that value. Y also you know. You substitute that value. You get that derivative value. Right? This value you got. You know current theta 100. You have calculated this value. Your alpha is a constant 0.0005. You can take, we'll talk about that later. I took some number there. Right? You can calculate next theta, right? Done?
Not exactly, sir, because you substituted 100 in place of x, but that's not the 100 is not the x value. It's the initial theta value.
Oh, sorry. 100 x, no, x is the, sorry, my bad. The x is like whatever the values are there in the data set, right?
Yeah.
For this particular record, you have
Yes.
values for all. That's what I'm trying to prove. I may get confused. X
Correct.
you have, y cap you have, y cap because theta is 100. X you already know, you substitute it, or you do theta transpose x, you get this value. You y you get, all the values are there. You know this value, you know this value, you know this value, you get next theta. Is this your question or something else?
Yeah, this is what my question is, because when we need to plot the graph, right, we need to know the theta and all.
So no need to do the plot. That's another thing.
No, theoretical I'm saying. No, we don't need to do that, but theoretical.
I actually took maybe around 1 or 2 days to do this whole thing. This is actually done done practically. Done practically. Even stochastic gradient descent also I did practically to show you clearly what is happening behind the scenes. This is the basis of whole AI. I would say whole AI. That whole AI is dependent on this one algorithm, this one solver. Okay. So you got this, right? So theta transpose x is the predictions of the data set. You get that clearly. Did you get it clearly? Theta transpose x is the predictions of the data.
Yes, sir.
Right? So I think we covered almost all of it in the gradient descent. Okay. Now let us look at this constant, this alpha. Right? In this formula, I have to explain only one thing, that is alpha. And I am taking some alpha here because if you look at this, and I need to move the theta in the direction of slope, right? In the direction of slope. So I need to subtract the 70,000. I need to subtract the slope or add the slope to the current theta. Okay, theta minus that slope. See this, it is actually 4,34,000 or 4,03,400, whatever. If you subtract 70, if you subtract 4 lakh number from 70, what happens? This theta will go somewhere, on that side, somewhere. And then the dot is actually going to go up, very up. Do you agree? If I don't have this constant, this multiplying constant here, what will happen? While calculating next theta, if I don't have this constant, multiplying constant, what will happen to next theta? What is the next theta number?
It's a big negative number.
It's a big negative number.
Negative number.
When it is a big negative number, what happens? This dot is going to be somewhere on top, right? So when it is somewhere on top, right, here the slope is 4 lakhs and I don't have this constant, and the next theta is equal to minus 4 lakh 3000, 370, right? So it's going to be around 80 something, right? 82 something, 83 something, right? So this is a negative number, so it's going to be somewhere here, and this line we need to make it like that, grow, and then there is going to be that dot. So there, this is the slope going to be higher than this here? Is the slope is going to be high or low here? Slope,
High, sir.
high, right? Slope here is high, here is a little low, and here 0. It's actually descending, right? If you go upright, the slope will go high. When you subtract, that's a high number from this number, again it will go up this side, again it will go up that side, again. No, instead of finding the best theta, you are actually going away from wherever you started from. You started with 100, you are going away because of not having this constant. To control the step size, right? What is that step size? We call it as, you started here, you took one step, you took another step, you took another step, like that you are taking steps and moving the theta to the global minima. To control the step, you use the alpha, right? So this is a hyperparameter, we call it as. We actually play with this. For this particular data set, this alpha is good. For other data set, maybe 0.001 is good. For other data set, maybe 0.003 is good. 0.01 is good. It is always between 0 and 1. To control the step size, this is the step size, and we are actually shrinking the step size in such a way that the algorithm moves towards global minima. This is called as learning rate. We are learning. We started with some 100, some number, and slowly we are learning and moving towards the global minima. Learning the best theta. What is learning in an algorithm? Coefficient is the learning. We are actually trying to learn the best coefficient. Step by step. We actually took this, this help of this constant to control that step. Got it? What is the use of alpha? Got it, right? Any questions?
So alpha will be varying for algorithm to algorithm, sir?
Data set to data set.
Data set.
Yeah, it is a hyperparameter. We need to tune, we need to choose, and we need to tune. I'll show example. In a code example, you will understand better. But theoretically, you understood, right? If you don't choose it, what happens? You understood, right? If you put it
Yes.
1, what happens? You understood. If you put it 0, if you put this 0, what happens? It will stay there only. At 70 only it will stay. Right? If you take this alpha 0, it will stay at 100 only. Wherever you started, it will stay there only. The theta will not move. Okay? So that is what here is happening. When you look at this total thing, ultimately at the end, The slope became 0. The coefficient is also kind of close to 0. So it is not moving anywhere. It's stuck there at the best fit line. Okay, it's stuck there at the best fit line. That is a beautiful algorithm. Actually, beautiful. You know, tomorrow we may not have class. Just do practice on the existing linear regression algorithm. On Friday, I'll try to explain stochastic gradient descent algorithm. Okay. So before we leave, right, I want to show you one video. See that? No, it is going to show you how exactly. That's how the algorithm is working. Now look at the right side graph and left side graph both. It is finding the slope. It is applying it. The line is moving. The linear regression algorithm, the line is moving. Again, finding the slope, applying it. Theta is equal to theta minus, current theta minus alpha into derivative. Finding the slope, applying it. Finding the slope, applying it. Finding the slope, applying it. Right? You see the applying formula here, the theta here. Right? That is how the algorithm is working. Visually, that is how. So when I took only 1x, 1y, 1 theta, I was able to do this graph. If I take 2 thetas, right, this diagram becomes a 3-dimensional graph, because here there is going to be theta 1, there is going to be a z-axis theta 0, and y-axis j of theta, and it is going to become a bowl, and it will be very difficult to visualize. Still moving. If you look at gradient, right, slope is reducing, right? This gradient is reducing, See that it reduced. It will reduce even more. So the algorithm, this formula is giving us that capability to move towards the global minima systematically. If you don't have this formula, right, you may do 1 million lines like these, but still you don't know where you are, whether you are at the best fit line or not. Got it? Any questions? Are we good? Are we good? Nobody is talking.
Yes, sir.
Should I run it again? Should I run it again?
No, sir, no, not required.
Not required, sir.
So that is gradient descent algorithm. And tomorrow, make it a practice session. Keshva is going to be there. Okay. And the day after tomorrow, I'll explain more on gradient descent algorithm. We need to understand